Complex compounds are a special class of compounds in which the metal atoms or ions are bound to a number of anions or neutral molecules. In modern terminology, these compounds are called coordination compounds. Coordination compounds or complex compounds are a type of addition compounds. When two or more stable compounds are allowed to combine in stoichiometric ratios, crystalline compounds are formed. These are known as addition or molecular compounds. For example, when saturated solutions of potassium sulfate and aluminium sulfate are mixed and heated till the crystallization point is reached, we get the well-known compound potash alum. Similarly, if we add a solution of potassium cyanide to a white precipitate of nickel cyanide, the precipitate immediately dissolves, and a red-orange solution of a new compound is obtained. On the basis of their nature, addition or molecular compounds are divided into two categories. They are double salts and coordination or complex compounds. Double salts are molecular compounds that are stable in the solid state but break down into individual constituents when dissolved in water. Note that the individual properties of the constituents are not lost in these compounds. For example, an aqueous solution of potash alum will give the tests for K+, Al+3 and SO4-2 ions. Other common examples of this class include carnallite and Moore's salt. On the other hand, coordination compounds are molecular compounds that retain their identity even when dissolved in water. Note that the individual properties of the constituents are lost in these compounds. For example, when potassium ferrocyanide is dissolved in water, it does not give the usual tests for Fe+2 and Cn- ions, indicating that the ion FeCN6-4 does not dissociate into Fe+2 and Cn- ions. Other familiar examples for nickel, copper, and silver are shown here. Actually, these ions are present in the form of a new ion called a complex ion. Compounds that have complex ions are called complex compounds. as the central metal ion in the complex ion forms dative or coordinate covalent bonds with the species surrounding it. Complex ions are also known as coordinate ions, and hence the corresponding compounds as coordinate compounds. Transition metals show a greater tendency to form complex compounds. This is due to the relatively smaller size of the metal ions, high ionic charges, and the availability of vacant d orbitals for bond formation. Coordination compounds form the backbone of modern inorganic and bioinorganic chemistry and chemical industry. Naturally occurring complex compounds are vital to living organisms. For example, chlorophyll is a coordination complex of magnesium. Hemoglobin is a coordination complex of iron. While vitamin B12 is a coordination complex of cobalt. Complex compounds find extensive use in electroplating, metallurgical processes, textile dyeing, and medicinal chemistry. Apart from that, they also find applications as industrial catalysts and analytical reagents. A coordination complex is the product of a Lewis acid-base reaction, in which a central metal atom or ion forms coordinate covalent bonds with neutral molecules or anions called ligands. Similar to the terms central metal and ligand, there are some other terms like coordination number, coordination sphere, coordination polyhedron, oxidation number, homoleptic complex, and heteroleptic complex, which are used with reference to coordinate compounds. Hence, you must get familiarized with these terms to understand different aspects of coordination chemistry. So let's go through these terms in detail. The first term is central metal atom or ion. The atom or ion to which one or more neutral molecules or anions are attached in a definite geometrical arrangement around it is called the central atom or ion. For example, the central metal ion in NiNH3 6 + 2 is Ni + 2, in FeCN6 - 3 is Fe + 3, and in COCl6 - 3, it is the CO + 3 ion. As the central metal atom or ion acts as an electron pair acceptor, it is also referred to as a Lewis acid. Another important term is ligand. A ligand is any atom, ion, or molecule capable of donating a pair of electrons to the central atom. A ligand is also known as a coordination group. As ligands are electron pair donors, they act as Lewis bases. Ligands may be simple ions such as halide ions, small molecules such as water or ammonia, or large molecules such as ethane 1,2-diamine or ethylene diamine tetraacetate ion. The number of atoms in a ligand that bind to the central atom in a complex is referred to as denticity. When a ligand is bound to a metal ion through a single donor atom, as with a chloride ion, a water molecule or an ammonia molecule, the ligand is said to be unidentate. Ligands that contain two donor atoms are known as bidentate or didentate. Common examples of didentate ligands are ethane 1,2-diamine, dimethyl-glyoxime, and oxalate ion. As you can see, these ligands have two donor atoms that can simultaneously bind to the central metal atom. Ligands with several donor atoms are called polydentate or multidentate ligands. A classic example of polydentate ligand is the hexadentate ligand, ethylene diamine tetraacetate ion, EDTA. You can see from its structure that it binds to the central metal ion through 2 nitrogen and 4 oxygen atoms. Ligands like ethylene diamine and EDTA, which have lone pairs of electrons on more than one atom, are capable of binding to the central metal atom or ion through more than one coordinate covalent bond. Such ligands are called chelating ligands. Some ligands have two different types of potential donor atoms, but use only one of them to form a coordinate covalent bond with the metal ion. Such ligands are called ambidentate ligands. The NO2- ion is one such ambidentate ligand capable of coordinating to the metal atom or ion through the nitrogen or oxygen atom. Similarly, the SCN- ion can coordinate through the sulfur or nitrogen atom. Now, let's look at another important term, coordination number. The total number of ligand donor atoms to which the metal is directly bonded is known as the coordination number of that ion. For example, the coordination number of silver in the complex ion AgNH32+ is 2, while that of nickel in the NiNH3 4+2 ion is 4. Similarly, the coordination number of copper in CuEn2+2, a complex with a didentate ligand, is 4, while that of cobalt in COC2O4 3-3, another complex with a didentate ligand, is 6. Coordination entity or coordination sphere is a common term we use with reference to complexes. The central metal atom and the ligands attached to it are collectively termed as the coordination sphere or coordination entity. For example, in the complex K4FeCN6, Fe, along with the 6 cyanide ligands, is the coordination sphere. the coordination sphere is written inside square brackets, while the ionizable groups are written outside the bracket and are called counterions. For example, in the complex K2NiCl4, the coordination sphere is NiCl4 minus 2, and the counterion is potassium. Coordination polyhedron is another term we use in coordination chemistry. In a coordination sphere or entity, the ligands are attached to the central metal ion in such a way that it gives a definite geometry to the complex. Thus, in a coordination entity, the solid figure defined by the position of the ligand atoms directly attached to the central atom or ion is known as the coordination polyhedron. The most common coordination polyhedra are octahedral, square planar, and tetrahedral. For example, CONH3 6 plus 3 is octahedral. NiCO4 is tetrahedral, while PtCl4 minus 2 is square planar. One of the most important terms we often use is oxidation number of the central atom. The oxidation number of the central metal atom in a complex is defined as the electric charge it would carry if all the ligands were removed along with the electron pairs that are shared with the central atom. The oxidation number is represented by a Roman numeral in parentheses after the name of the central metal atom. For example, the oxidation number of iron in FeCN6-3 is plus 3, and it is written as Fe3. Let us learn the method to determine the oxidation number of the central metal atom in a complex. Let's take K4FeCN6 as an example. As the complex has 4 monovalent cations outside the coordination sphere, the complex ion carries a charge of minus 4, that is, FeCN6 minus 4. Let's assume the oxidation number of the central metal atom as X. The cyanide ion is a monodentate negative ion. Knowing that the complex carries a charge of minus 4 and has 6 monodentate negative ions, the oxidation number of iron can be determined as X plus 6 multiplied by minus 1, which is equal to minus 4. On simplification, we get X is equal to plus 2. Thus, the oxidation state of iron in the given complex is plus 2. Here is a simple problem for you. Calculate the oxidation number of the metal atoms in the complexes given here. In the first case, there are 3 cations outside the coordination sphere. Hence, the charge on the complex ion is minus 3. The oxalate ion is a bidentate ligand. Each oxalate ion carries a charge of minus 2. The oxidation number of iron, which is assumed as X, is calculated as X plus 3 multiplied by minus 2, which is equal to minus 3. On simplification, we get X is equal to plus 3. Hence, the oxidation number of iron is plus 3. Similarly, the oxidation number of copper and silver in the other two complexes are calculated as +2 and +1 as shown. Finally, let's look at the terms homoleptic complex and heteroleptic complex. A complex in which a metal is bound to only one type of ligand atoms is known as a homoleptic complex. For example, CONH3 6 + 3 and FeCN 6 - 3. On the other hand, a complex in which a metal is bound to more than one kind of ligand atoms is called a heteroleptic complex. For example, CONH3 4ClBr +1 and CrNH3 4Cl2 +1. Have you ever wondered why a stable salt, such as cobalt trichloride, combines with a group of stable, independently existing molecules, such as ammonia, to form new compounds like COCl3, 6NH3, COCl3, 5NH3, and COCl3, 4NH3 with entirely new properties? Alfred Werner, a Swiss chemist, after preparing thousands of new compounds and studying their properties, put forward a theory to explain the formation of complex compounds. It was the first successful explanation for the phenomenon. The theory became famous as the coordination theory of complex compounds, which is also known as Werner's theory. His explanation of complex formation is based on some postulates. The first postulate is that the central metal atom or ion in a coordination compound exhibits two types of valencies, primary and secondary. While writing the structure of the metal complexes, the ligands that are linked by primary valency are shown by dotted lines, while those linked by a secondary valency are shown by thick lines. If a ligand satisfies both the valencies, then it is shown by a thick as well as by a dotted line, and it is said to exhibit dual character. The second postulate is that primary valencies are ionizable and correspond to the number of charges on the complex ion. Primary valencies apply equally well to simple salts and to complexes, and are satisfied by negative ions. For example, the primary valency of 2 in COCl2 is satisfied by 2 chloride ions. Similarly, the primary valency of 3 in the complex CONH3 6Cl3 is satisfied by 3 chloride ions. In modern terminology, the primary valency corresponds to the oxidation number. The third postulate is that secondary valencies correspond to the valencies that a metal atom or ion exercises towards neutral molecules or negative ions in the formation of its complex ions. Every metal has a fixed number of secondary valencies or coordination number. For example, cobalt 3+, platinum 4+, and iron 3 plus ions are recognized to have a coordination number of 6. Similarly, nickel 2 plus, copper 2 plus, and platinum 2 plus ions have a coordination number of 4. Secondary valencies are non-ionizable. They are satisfied by neutral molecules or negative ions. The secondary valency is equal to the coordination number of the metal. For example, in the complex COCl3 6NH3, the 3 chlorides are held by primary valencies and the 6 ammonia ligands are held by secondary valencies. The fourth postulate is that secondary valencies are directional, and so a complex has a particular shape. The number and arrangement of ligands in space determines the stereochemistry of a complex. The most common coordination number in transition metal complexes is 6. And the shape is usually octahedral. The coordination number 4 is also common, and this gives rise to either tetrahedral or square planar complexes. This postulate predicted the existence of isomerism in coordination compounds. To distinguish between the two types of valencies, Werner introduced the concept of using square brackets to enclose the atoms that make up a coordination complex and which are, therefore, not ionized. The postulates of Werner's coordination theory were actually based on experimental evidence rather than theoretical. Werner treated cold solutions of a series of compounds of cobalt 3 chloride with ammonia with an excess of silver nitrate and weighed the silver chloride precipitated. The stoichiometries of the complex silver chloride formed were as shown here. Werner deduced that in COCl3 6NH3, the primary valency or oxidation state of +3 is satisfied by 3 chloride ions. The coordination number of the cobalt 3 plus ion is 6. As there are 6 ammonia molecules in the compound, they alone satisfy the 6 secondary valencies of cobalt. As you can see, the primary valencies are represented by dotted lines and the secondary valencies by thick lines. In modern terms, the complex is written as CONH3 6Cl3. The 3 chloride ions are ionic and hence are precipitated as silver chloride by silver nitrate. Thus, the complex will ionize in solution and give 4 ions. That is, 1 CONH3 3 plus ion and 3 chloride ions. Werner deduced that the loss of one ammonia molecule from COCl3, 6NH3, should give COCl3, 5NH3. This complex has only 5 ammonia molecules. Therefore, to satisfy the coordination number of 6 of cobalt, one chloride ion assumes dual behavior. That is, it satisfies the primary as well as the secondary valency of cobalt. In modern terms, the complex can be written as CONH3 5Cl Cl2. Thus, only 2 of the 3 chloride ions are ionic, and thus only 2 are precipitated as silver chloride with silver nitrate. On ionization, this complex will give 3 ions: 1 CONH3 5Cl 2 plus ion and 2 chloride ions. As can be seen from its structure, one chloride ion, which is playing a dual role, is shown by a thick as well as a dotted line. Similarly, in COCl3, 4NH3, to satisfy the secondary valency of 6, 2 chloride ions assume dual behavior. In modern terms, the complex can be written as CONH3 4Cl2 Cl. Thus, only one chloride ion can be precipitated as silver chloride. This complex, on ionization, gives 2 ions: one of CONH3 4Cl2 plus and the other of chloride ion. The structure of the complex is shown here. Although Werner's theory successfully explains the bonding features in coordination compounds, it suffers from some drawbacks. It doesn't explain why only certain elements form coordination compounds. It does not explain why the bonds in coordination compounds have directional properties. It does not explain the color and the magnetic and optical properties of complexes.